Okay, kinetic theory.
They have low densities.
Yes, they have low density. क्यों low density होती है उनकी?
Mass negligible मानते हैं और वॉल्यूम negligible मानते हैं.
क्योंकि हम gases को compress कर सकते हैं, which really signifies it has lot of spaces between them. That is why we consider it that its density is very low, right? और क्या reason है? और क्या था assumption? They are always colliding with each other as well as with the walls of the container. The collisions are elastic. Kinetic energy depends upon the absolute temperature of the gas. Right? Volume negligible. Interaction between them is negligible. There is no interaction. Repulsive, attractive, कोई interaction नहीं है gaseous molecule में. समझ रहे हो? We're following kinetic theory of molecules में assumptions दिए गए, ठीक है, जिससे कि हम प्रूव कर सके certain PV is equal to nRT को हम प्रूव कर सके. इसकी वजह से kinetic energy of molecules में assumptions दिए गए. तो उसने assumptions करे थे. किसने करे थे? मैक्सवेल, बोल्ट्जमैन, दो साइंटिस्ट थे. Separately, together they worked on it and they made certain assumptions. जब assumptions करे थे तो क्या क्या assumptions करे थे? सबसे पहली चीज वॉल्यूम इज नेग्लिजिबल. क्योंकि वॉल्यूम क्यों नेग्लिजिबल है? इतना छोटा मॉलिक्यूल है, इतना छोटा मॉलिक्यूल है, वो जितना वॉल्यूम ऑक्यूपाई करेगा वो ना के बराबर होगा. फर्स्ट. सेकेंड थिंग, वो आपस में कोलॉइड करेंगे. आपस में कोलॉइड करेंगे. इसमें चलते बंद करवाया था. सो आपस में कोलॉइड करेंगे एंड दे विल आल्सो कोलॉइड विद द वॉल्स ऑफ द कंटेनर. और जो भी कोलिजन होगा इलास्टिक होगा. व्हाट डू मीन बाय इलास्टिक? देयर विल बी नो लॉस टू एनी अदर. एक ने जो लॉस किया दूसरा गेन करेगा. कोई और जगह पे लॉस नहीं होगा, ठीक है. और तीसरी चीज हमने काइनेटिक एनर्जी जो होगी मॉलिक्यूल की वो टेम्परेचर का फंक्शन है. ये तीन चीजें पढ़ी हमने. तो हमने इफ यू रिमेम्बर वी स्टडीड दिस ग्राफ, राइट? वी स्टडीड दिस ग्राफ. अब इस ग्राफ में क्या बता रहे हैं? ये देखो, आपका वाई एक्सिस में फ्रैक्शन ऑफ मॉलिक्यूल्स बता रहे हैं. एक्स एक्सिस में यहाँ पे काइनेटिक एनर्जी है. आप स्पीड भी प्लॉट करोगे तो आपको सेम टाइप ऑफ ग्राफ मिलेगा, ठीक है. तो अब जब इस ग्राफ को प्लॉट कर रहे हैं तो हम ये देख रहे हैं कितने मॉलिक्यूल्स के पास कितनी स्पीड है या कितनी एनर्जी है. तो जब मैं प्लॉट करती हूँ तो मुझे ये पता चलता है T1 टेम्परेचर का जो प्लॉट है, आई सी दैट जो मैक्सिमम नंबर ऑफ कंपाउंड मॉलिक्यूल्स प्रेजेंट है उस गैस में, उनकी जो स्पीड है वो मोस्ट प्रोबेबल स्पीड यहाँ पे लाई करती है, जो मैक्सिमम अमाउंट है. क्योंकि मैं क्या कह रही हूँ, हर किसी की वेलोसिटी डिफरेंट होती है. जैसे एक कंटेनर में अगर गैस मॉलिक्यूल्स प्रेजेंट हैं, ठीक है, हर एक की वेलोसिटी अलग है. हर एक की वेलोसिटी अलग है. तो मैं हर एक की जो वेलोसिटी अलग होगी तो जो मैं प्लॉट करूँगी, कुछ की ज़्यादा आएगी, कुछ की कम आएगी, तो उसका जो ग्राफ आएगा वो ऐसा रेड वाला जो ग्राफ शो कर रखा है वो आएगा. तो उसमें क्या होगा? मोस्ट प्रोबेबल स्पीड यहाँ पर है, एक एवरेज स्पीड होगी और एक आएगी RMS स्पीड. RMS रूट मीन स्क्वायर स्पीड, ठीक है. अब मैंने एक और चीज क्या पढ़ी थी? टेम्परेचर इंक्रीज करने में ये जो थंब है ब्रॉड हो जाता है. क्यों? जब मैं टेम्परेचर इंक्रीज कर रही हूँ मॉलिक्यूल्स का कोलिजन और बढ़ेगा. जब कोलिजन और बढ़ेगा तो वेलोसिटी बढ़ेगी, स्पीड बढ़ेगी. जब स्पीड बढ़ेगी तो और जो मॉलिक्यूल्स हैं, यहाँ पे क्या थे कम स्पीड वाले मॉलिक्यूल और ज़्यादा वाली स्पीड में चले गए, जिसकी वजह से क्या हुआ, मेरा जो एरिया अंडर द कर्व है वो ब्रॉडन हो गया. तो तीन चीज़ें होती है टेम्परेचर इंक्रीज करने. मोस्ट प्रोबेबल स्पीड इंक्रीज हो जाएगी, एवरेज भी इंक्रीज हो जाएगा, आरएमएस भी इंक्रीज हो जाएगा, तीनों चीजें इंक्रीज होंगी। डिस्ट्रीब्यूशन ब्रॉडन, देखो बड़ा हो गया एरिया, ठीक है। नंबर ऑफ मॉलिक्यूल मूविंग विथ हायर स्पीड इंक्रीजेस। अब मेरी हायर स्पीड तो इस रीजन में होगी, अगर मैं चेक करूँ तो ये देखो इतना बड़ा एरिया बन गया, सो दैट मीन्स इतने सारे मॉलिक्यूल्स के पास वो हायर स्पीड है। तो दिस इज व्हाट माय ग्राफ सजेस्ट। अब नाउ द होमवर्क व्हिच आई गिव यू, व्हिच यू डिडंट डू, व्हिच आई डिड फॉर दैट मैटर, ठीक है। The most probable speed of a gas in the masses at which the distribution of the graph reaches its maximum. That is the thing. How do I calculate it? This is the formula to calculate. The square root of 2RT upon M. 2RT upon M means R here is real gas constant, temperature of the gas, and M is the molar mass of the gas. So how it is related? It is directly proportional to the temperature and inversely proportional to the molar mass. So higher is the molar mass, average most probable क्या होना चाहिए, कम होगा, right? Higher is the temperature, speed ज़्यादा होगी। ये दोनों रिलेशनशिप याद रखना, क्योंकि देखो तुम लोग नीट के लिए प्रिपेयर कर, नीट में क्या आते हैं आपको सॉल्व करने वाले क्वेश्चंस, कैलकुलेशन वाले क्वेश्चंस कम आते हैं, थियोरेटिकल क्वेश्चन ज़्यादा आते हैं। जब आप फोकस कर, ये नहीं कह रही कि नहीं आएंगे, पर कैलकुलेशन भी सिंपल वाली आती है और मोस्ट ऑफ दी ऐसे एप्लीकेटिव क्वेश्चन आते हैं। फोकस करके स्टडी करोगे फर्स्ट अटेम्प्ट में भी निकल सकते, राइट। सो क्या है, माई UMP इज प्रोपोर्शनल टू टेम्परेचर एज वेल इनवर्सली प्रोपोर्शनल टू मोलर मास. What is it defined by? The maximum in that hump. Similarly, average speed, if I come across, what is average speed? Average speed is mean of all the magnitudes of velocity. So that means U average is equal to U1 plus U2 plus U3 up to UN divided by N. This is my U average, and in terms of your temperature and molecular mass, it is represented by 8RT pi m, square root of 8RT pi m. ठीक है, सो मोस्ट प्रोबेबल हो गया, एवरेज स्पीड हो गया। अब क्या तीसरी चीज बची हमारी, रूट मीन स्क्वायर स्पीड। रूट मीन स्क्वायर स्पीड, तो रूट मीन स्क्वायर स्पीड क्या होगी? सो बेसिकली व्हाट इज इट? इट इज बेसिकली एवरेज का रूट मीन स्क्वायर। अगर इफ आई कैलकुलेटेड just average the root mean square, so its theoretical value can be calculated. So you can see all these speeds are directly proportional to the temperature and inversely proportional to the molar mass. So if the four gases are given, CO2, O2, H2 and Cl2, which one would have highest most probable speed? How will you say that? मोलर मास। तो क्या मैं चार ऑप्शन दिए आपको, Cl2, O2, H2 एंड CO2। ये चार ऑप्शन में किसका सबसे ज्यादा मोस्ट प्रोबेबल स्पीड होगा? हाउ इज इट रिलेटेड? 1/m मॉलिक्यूलर मास। सो मॉलिक्यूलर मास जितना ज्यादा होगा स्पीड उतनी कम होगी। तो इनमें से किसका सबसे कम मोलर मास होगा, उसका सबसे ज्यादा होगा कम मोलर मास, H2. So this would have the highest, most probable, which would have the highest? डाउट नहीं होना चाहिए।
I was calculating.
हाँ, Cl2 will have the highest. अब now I asked for a relationship between, and ये क्वेश्चन बार बार पूछा जाता है। कैसे पूछा जाता है ये याद देखते हैं। इधर आपको बोलेंगे 4 ऑप्शन दे देंगे और इनको आगे पीछे कर देंगे, ठीक है? आगे पीछे कर दिया मतलब U average to U MP to U RMS, तो then it will become 1.128 is to 1 is to 1.1224, ठीक है? तो ये रिलेशनशिप जिस ऑर्डर में तुम याद करना चाहो तुम अपना कन्वीनियंस दो। उसके अलावा कैसा क्वेश्चन आ सकता है, U एवरेज दे दिया, U MP फाइंड कर लो। ये रिलेशनशिप पता है, आराम से कर लो। ये रिलेशनशिप याद रहना चाहिए। ये रिलेशनशिप याद रहेगा तो मेरे को U RMS दे दे, U एवरेज पता करने को बोल दे, U MP दे दे, मुझे U एवरेज पता करने को, कुछ भी पता करने के लिए मुझे बस ये रिलेशनशिप को जरूर याद रखना है। क्लियर?
हम 11th में नीट में सबसे ज़्यादा चैप्टर किस मतलब
केमिकल बॉन्डिंग।
केमिकल बॉन्डिंग कितने मार्क्स है?
8 का तो है।
8 कितना?
8 क्वेश्चंस तो एक्सपेक्टेड होते हैं।
8 क्वेश्चंस
मतलब डिपेंड करता है, बट जनरल ऑर्गेनिक केमिस्ट्री से सिर्फ 1 क्वेश्चन एक्सपेक्टेड है।
जो जो दूसरी बुक है,
हाँ,
उसमें से
एक मतलब उसका फर्स्ट चैप्टर से जनरल ऑर्गेनिक में उसमें सिर्फ एक ही क्वेश्चन एक्सपेक्टेड है। आईपैक नहीं आ जाएगा या कोई इफेक्ट, पर बहुत बड़ा चैप्टर है, वो नहीं पढ़ा तो बाकी पूरा ऑर्गेनिक नहीं पढ़ सकते। तो पढ़ना बहुत ज़रूरी होता है। आएगा एक, क्योंकि उसी का एप्लीकेशन बाकी चैप्टर्स में है। वो चैप्टर नहीं आया,
स्ट्रक्चर ऑफ एटम से कितना आता है?
स्ट्रक्चर ऑफ एटम से ज़्यादा नहीं आते। केमिकल बॉन्डिंग मोस्ट, states of matter is most, thermodynamics is most, chemical bonding सबसे ज़्यादा है, ठीक है? अब हम आगे बढ़ते हैं। कहाँ? रियल गैस पे। अभी तक आइडियल कर लिया। अब रियल गैस का मतलब क्या हुआ? मैं क्या बोलना चाहती हूँ, इन नेचर में, इन दिस नेचर आइडियल सिचुएशन कोई फॉलो नहीं करता, जैसे हम भी फॉलो नहीं करते आइडियल सिचुएशन। एक स्ट्रिक्ट रूटीन रखने की कोशिश करते हैं कि इतने घंटे पढ़ना है रोज, पर हम फॉलो नहीं कर पाते। इतने घंटे खाना है, इतने घंटे सोना है, हम नहीं फॉलो कर पाते। ऐसे ही गैसेस भी आइडियल कंडीशन फॉलो नहीं कर पाते। शायद तब कर ले, तुम लोग तब कर लो जब पेपर बहुत पास आ जाए, तो बहुत स्ट्रिक्ट हो जाओ अपने साथ, बहुत स्ट्रिक्ट डिसिप्लिन। तो ऐसी एक कंडीशन होगी इनके साथ भी जिधर वो फॉलो कर सकते हैं, वो भी देखेंगे हम। तो क्या कहना चाहती हूँ मैं, एक स्ट्रिक्ट कंडीशन अप्लाई कर दो तो शायद फॉलो कर ले, पर मोस्ट ऑफ द केसेस में नहीं फॉलो कर रहे। तो क्या चीज़ नहीं फॉलो कर रहे? जो हमने 4 लॉस पढ़े थे, कौन कौन से लॉस पढ़े थे? बॉयल्स लॉ, चार्ल्स लॉ, Gay-Lussac law and Avogadro law। So ये चारों लॉ फॉलो नहीं कर रहा है। अब ये फॉलो क्यों नहीं कर रहा है वो हम समझेंगे। यहाँ पे हमारी क्या है, क्या समझ रहे हैं कि ये जो अजम्पशंस जो हमने लिए थे, इंटरैक्शन नहीं है, वॉल्यूम नेग्लिजिबल है, सब कुछ जो हमने अजम्पशन किया था उनमें से कुछ अजम्पशंस नहीं वैलिड हुए, जिसकी वजह से डिविएशन हुआ। तो ये डिविएशन, रियल गैसेस डू नॉट फॉलो द परफेक्ट गैस लॉ एग्जैक्टली बिकॉज मॉलिक्यूल्स इंटरैक्ट विद ईच अदर। उधर क्या बोला था? देयर इज नो अट्रैक्टिव फोर्सेस, नो रिपल्सिव फोर्सेस, बट हम क्या बोल रहे हैं? इन नेचर दे डू इंटरैक्ट। हमने इंटरमॉलिक्यूलर फोर्सेस पढ़ी हैं, राइट? गैसेस के बीच में भी हो सकती हैं। सो दोनों फोर्सेस एग्जिस्ट करती हैं, repulsive and attractive, right? Now let's try to see and analyze the situation. Repulsive forces कौन सी होंगी, attractive forces कौन सी होंगी? रिपल्सिव फोर्सेस कौन सी होंगी? जो मॉलिक्यूल असिस्ट करेगा एक्सपेंशन में, राइट? कैसे? रिपल्सिव फोर्सेस की वजह से वो एक दूसरे को रिपेल करेंगे तो वो एक्सपैंड करेगा गैस, राइट? क्योंकि वो आपस को रिपेल कर रहे हैं तो वो बोलेगा कि मुझे इधर नहीं रहना। जैसे एक सिचुएशन समझ लो, यहाँ की सिचुएशन समझ लो, तुम दोनों को साथ में नहीं बैठना, यू शिफ्ट हियर, सो दैट मीन्स यू आर एक्सपैंडिंग। सिमिलर टाइप, सो अट्रैक्टिव फोर्सेस क्या करेंगे? दैट विल कॉज कॉन्ट्रैक्शन। अगर कुछ किसी के बीच में गुड, जैसे if situation, if you guys are best friend, then you will try to stick together, try to go to the classes together, try to find places where your seats are closer. So that is compression I'm doing, right? So that is what repulsive forces causes the expansion, attractive forces causes the molecule to come closer to each other. These are the molecular interaction which we are talking about. So in order to understand this molecular interaction, then the compression factor Z was introduced. The compression factor Z is introduced. What is this Z is? Z is basically equal to PV upon RT. For the ideal situation, the Z becomes equals to 1. Then I get this equation, PV is equal to nRT. But all other real gas situation, either Z would be greater than 1 or less than 1. Either it is greater than 1 or less than 1. It can be either of the cases. So for the perfect gas, Z is equal to 1 under all conditions. The deviation of Z from 1 is a measure of departure from the perfect behavior. That is when the gas is behaving like a real gas, not as an ideal gas, right? So if I try to plot it, let's say I'm trying to plot. So when I'm plotting PV versus V isotherm. So PV is on your y-axis, pressure on the x-axis. So when I'm plotting ideal gas, Z is equal to 1. So that means that will have a straight line, PV by T. Okay, it should have a straight line. But what do I see? These are the four gases example which I have taken: helium, hydrogen, methane, and carbon monoxide. So what do I see in this? I see that there is positive deviation in the case of H2 and He. So that is helium and hydrogen. What's the? So if you plot Boyle's law, PV is equal to K होता है, right? So PV versus P, if you plot it in the Boyle's law, you'll get a straight line. This is PV isotherm. Isotherm is like a graph. That is what. So whatever the relationship, that is what is written PV with P isotherm.
Pressure into volume with pressure.
Yes, if you are plotting it, then for the ideal gas you should get straight line. But as I know in nature, no gas follows the ideality at all conditions. So what type of deviation I am observing in each of the gases, that is what I am trying to plot. So when I see hydrogen and helium, it shows positive deviation. That is, it's going above the ideal situation. So it's showing positive deviation. On the contrary, if I see carbon monoxide and CH4, they are showing first negative deviation. First part is negative and then positive deviation. Are you able to see?
So it first says that when the pressure is very
When the pressure is low, there is a dip. That is, there is a negative deviation. Ideal situation से negative जा रहा है. Z is less than 1. जब ideal situation से ऊपर जा रहा है, Z is greater than 1. समझ आया? PV तभी बढ़ेगा ना. Z का relationship क्या है? Z is equal to PV upon RT, right? So PV बढ़ेगा तो that means Z will become greater than 1. Z की वैल्यू 1 है, अगर मेरा न्यूमरेटर बढ़ रहा है तो ऑब्वियसली उसकी वैल्यू बढ़ेगी. क्लियर? दिस आइसोथर्म इज क्लियर. अब अगर मैं इसी को प्रेशर वॉल्यूम की तरह मैं प्लॉट करूं जो मैं करती हूँ बॉयल्स लॉ में, तो आइडियल सिचुएशन, रियल गैस सिचुएशन. So there is a merging up which is happening at this place. There is a merging up. So at certain condition, low pressure, this condition, then this gas does behave as ideally as well. Clear so far? Picture is clear. So in order to correct the real ideal gas equation, we introduced the correction factor to the ideal gas equation. So in order to fan चलाना
तेज करना है.
यहाँ पे तेज हवा आ रही थी मुझे. So अब अगर डिविएशन हो रहा है तो दो पैरामीटर्स है, दो assumptions है जिसकी वजह से डिविएशन हो रहा है. There is no force of attraction between the molecules of a gas. Volume of the molecule of a gas is negligible by the in comparison to the space occupied. So assumption A wrong prove क्यों हुआ? Assumption A, there is no force of attraction. आपको पता है मैं गैस को कंप्रेस करती जाऊँ मैं उसे लिक्विड फॉर्म में लेकर आ सकती हूँ. कार्बन डाइऑक्साइड लिक्विड, नाइट्रोजन लिक्विड एग्जिस्ट करता है नेचर में. लिक्विड नाइट्रोजन, लिक्विड CO2 सब एग्जिस्ट करता है. तो अगर ये अट्रैक्टिव फोर्सेस नहीं हो, लिक्विड विद इंटरेक्शन है सॉलिड में और सॉलिड CO2 भी अवेलेबल है, तो अगर मेरे अंदर मैं कहती कि कोई इंटरेक्शन नहीं है तो मैं कभी लिक्विफाई नहीं कर सकती थी किसी भी गैस. मैं लिक्विफाई कर सकती हूँ, इस वजह से क्या है मेरा assumption A wrong होता है. If I cool down the temperature, I can liquefy the gases. That is why there is no attraction between the molecules of a gas is proved wrong. Similarly, assumption B is correct. The pressure versus volume graph, experimental data that theoretically calculated Boyle's data should coincide. So when we saw this, they are coinciding with one another. That is what the assumption 2, which was correct. Clear? So now I am going to modify my equation. How am I going to modify it? I am going to introduce P plus delta P, V minus delta V into it, so that my ideal gas equation gets modified to form for the application for real gas situation. Yes. So ये जो correction factor मैं introduce कराऊंगी ideal situation में, based on the fact that they occupy volume and they have interaction. ठीक है? तो what are the two important factor which was introduced? This was it, Van der Waal equation. This is what it is, the main equation which was observed. So how it is being, so this is my P ideal and this is the correction factor. Similarly, this is my V ideal and this is the correction factor. So what is the correction factor? A n square upon b square, and here nb, where this A and B are the constant which is different for every gas. So A and B की वैल्यू आपको टेक्स्ट बुक में दे रखी है हर एक गैस के करस्पॉन्डिंग. ठीक है? हाँ, नहीं करनी, बिल्कुल नहीं करनी. आपको क्वेश्चन में भी दिया गया होगा अगर क्वेश्चन आता है तो. वैसे कैलकुलेशन पॉइंट ऑफ व्यू से नहीं आता है, पर हाँ ये ज़रूर आता है What do they depend upon? What do they depend upon? A depends upon size and polarity. You have to remember. So that is molecular interaction it depends upon. It depends upon the molecular interaction. So if at all a question arises stating that what are A and B in the real gas equation depends upon. Then option 1 of the option would be molecular interaction. Clear? Or else what is the term which it is modified with? A n square upon V square. How is the pressure modified? Or how is the volume modified? N into B. So these kind of questions do arise. Now we come to one of the greatest discovery of Andrews isotherm. Before understanding Andrews isotherm, just try to understand certain things. So I know gas can be liquefied. I've just learned it, the gases can be liquefied. But there is a temperature above which you cannot liquefy that gas. There is a temperature above which you cannot liquefy a gas. In order to understand that, so Andrews is a scientist who proposed this isotherm where pressure versus volume. This is for the carbon dioxide. This graph is for carbon dioxide. I know it looks really messy when you see it this way. I'll break down this graph for you so that you can actually understand what exactly is happening, and I'll arrive at this graph only. So this is my pressure, this is my volume. Okay. So the hump which is mentioned over here, this is liquid which is in equilibrium with gaseous molecule. This side it is liquid, this side it is gaseous. This much is clear. This is my isotherm, in which there is a region in which, so you know, right, at particular temperature there is a phase transformation occurring. Wherever there is a phase transformation occurring, there is an equilibrium condition in which liquid and gaseous molecule will lie together.
So low volume means like this very less space, so it's being present as a liquid.
Yes.
So, and there's a period during which it's both liquid and gas.
Both coexist with one another. So if you remember in the previous classes, you have studied about the phase transformation graph, which goes like this. So this phase represents melting, this phase represents boiling. Remember, phase solid, solid, solid. Then you reach a temperature at which solid is getting converted into liquid. The temperature remains constant. Then again, when you increase the temperature, then again the liquid to gaseous, the boiling point and the melting points are reached. Remember?
Yes,
No.
Yes, one latent.
Yes. Do you remember?
Yes.
So, what would happen? So now, first temperature which I am starting at 13.1 degrees Celsius. So let's say I am starting at 13.1 degrees Celsius. So here I am reaching, I am encountering this isotherm. So in which it's going to exist in liquid and gaseous phase, and then above this it will be liquid phase. So this is which one? Your so let's say this one, the blue line one. This is your blue line one, 13.1 degrees Celsius. Let's say I increase the temperature to 21.5 degrees Celsius. Again, it will go like this, and then a straight line, and then like this. Fine. Then there comes a temperature. Where it's going to touch the tip of it. That is your 30.98. So this 30.98 degrees Celsius is the critical temperature. Now, critical temperature. So that means if I am going to increase the temperature from 30.98 to 31, then it will not be liquefied, it will exist as a gaseous molecule only. So this portion is not completely liquid, understand that. So when I mention liquid, it's going till this region only. There is no specificity stating that the liquid will be existing like this. So what is certain, that here it is gaseous, here together they are existing, and here it is liquid in nature. But as soon as when I increase the temperature, it's not touching the hump. So that means it remains as a gaseous molecule only.
But it's entering that side.
No. So that is what Andrews isotherm is about. Until unless that hump is touched, it will not be liquefied.
But we are considering the left side.
We are not considering. I just mentioned it that this portion side of it is liquid, stating that when I encounter that hump, after that it is liquid in state. So as soon as I increase the temperature from 30.98 degree to 31, so there is no liquefaction. So further, so that means above my critical temperature, gas is behaving ideally. Yes, no compression is occurring. So at high temperature, the gases behave ideally, right?
All the theories.
Yes. So then that means there comes a temperature, critical temperature, wherein that is the upper limit. Above that temperature, no liquefaction process can occur for a particular gas. At that particular, the volume, critical volume and critical pressure. I can have three terms: critical volume, critical pressure and your critical temperature, depending upon. So let's say the type of question which, so I am going to see the question point of view, how it is going to arise. What is it going to arise? There will be two gases which will be given to you. Let's say ammonia and carbon monoxide. So let's say carbon monoxide has a critical temperature of 500 Kelvin and ammonia has a critical temperature of 350 Kelvin. Okay? This is not real value. I've just assumed a question. So this is the data, and you're being said that you're coming down from 700 Kelvin. Which gas will liquefy first? That's your question. Both of them will liquefy at the same time. CO will liquefy first.
CO will liquefy.
Ammonia will liquefy first. CO. Why CO?
Because now it's coming down from 700, so now
Yes.
it will reach 500 first.
Yes.
And 500 is the critical temperature for CO.
Yes.
So
It will liquefy. Did you understood? So why did he choose liquid? So which one will liquefy later? NH3, right? So this is the very famous question which actually can arise from Andrews isotherm, stating that two temperatures are given to you of the two gaseous molecules. Which one of them will liquefy faster or sooner or first, or all these terminology can be used. And you will be given the critical temperature of each one of them. So what is Andrews isotherm basically telling me? It is giving me the critical temperature of a gas above which the gases cannot be liquefied. That is what my Andrews isotherm is saying. So carbon dioxide is a gaseous state up to 73 atmospheric temperature of 30.98. It converts into liquid state, pressure at 73 and 30. So this is my critical pressure. This is my critical temperature. The pressure is called the critical pressure and this is referred as critical temperature. At this critical temperature and pressure, the volume of 1 mole of a gas is known as critical volume. Clear? All the three terminology is clear. Andrews isotherm is clear. People find, so this graph became simpler to understand now. Fine, because I know looking at this graph anybody would get scared. What is this graph, right? So when we simplify it, how do we simplify it? We went from 1 temperature to increase. When we increase the temperature, we saw the graph is shifted above and they reached a point where it touched the hump of that isotherm. Clear?
Yes.
Proceeding further, then if this is clear, this is the kind of graph which you have studied in lower class. Solid on the one side, liquid on the other side, the gaseous on the other side. Remember? This is the kind of graph. So then there comes a question. Have you heard of the point triple point? Don't say that. You have heard about that. Triple point. The triple point. This triple point is co-junction of all the three states. Remember? Critical pressure, the triple point of a substance is the temperature and pressure at which it can exist in all three states.
How can it, ma'am, exist in all three states? Ma'am, it sounds
Impossible for us to imagine. But there are proofs and validations and the experiments which have been conducted, and if you pursue chemistry, the physical chemistry or the physics in the future, you can deal with it and perform these experiments. So I give you one such example, Diels-Alder's reaction. I used to study that. I was like, how's that bond looks like? Okay, Diels-Alder reaction. It is like this. Mix these two. No need for any reagent or anything. Mix these two. Put them in an autoclave and high temperature and pressure. What would happen? It would result in the formation of this. मैंने बोला ऐसे ही डंडे जुड़ के एक रिंग बना देंगे. I used to think like this. अरे ये सब पेपर में लिखने के लिए रिएक्शन है. ऐसे थोड़ी ना हो जाएगी रिएक्शन. कोई मैकेनिज्म नहीं, कुछ नहीं, कोई चार्ज ट्रांसफर नहीं हो रहा, कोई रिएजेंट नहीं ऐड किया, एसिड ऐड करो या फिर कोई ऑक्सीडाइजिंग एजेंट ऐड करो, कुछ तो ऐड करोगे, राइट? आई यूज्ड टू थिंक इट. आई एम इन द सिमिलर शूज लाइक यू. आई डिड दिस एक्सपेरिमेंट ऑन माय ओन in the lab. I did perform the Diels-Alder reaction. This reaction is referred by the name Diels-Alder's reaction. It doesn't require any reagent, any solvent. In order to dissolve also it doesn't. Put it together, whether they dissolve with one another or not, it doesn't really matter. Put it together, seal the vessel, put it for heating, this reaction will occur. It's very impossible right now when I say it, right? For you as well. But if you go further in the future to pursue science,
what's the state of these two things?
These two, liquid.
Then ma'am, you mix and you're taking two liquids, ma'am, what's ma'am not? How can this dissolve?
That is what's happening. That is how the reaction is happening. So this is basically shifting to here, this is shifting to here, and this is shifting to here. So the new bonds are getting formed and only you are left with one level of unsaturation. Here you have three levels of unsaturation. So in the similar manner, this triple point, which cannot be explained theoretically to you, but when you perform it in the practical situation, this does exist.
So for now we just have to know.
Yes. So until unless you're going to perform an experiment in your lab, and if your lab is that equipped that it can provide you that particular situation.
Ma'am, does this Diels-Alder one require any equipment?
Yes, it does.
Ma'am, I mean, you just have
Autoclave.
to
You require autoclave for that. Autoclave.
What's that?
So pressure cooker सुना है? Pressure cooker में under pressure आपका चीजें जल्दी पक जाती हैं, right? आप pressure तो हमें ज़्यादा हीट, तो अगर मैं खुले में दाल उबालूँ खुले पतीले में और प्रेशर कुकर में उबालूँ, आधा टाइम भी नहीं लगता। क्यों? क्योंकि मैं अपना प्रेशर कम कर रही हूँ, तो वाटर को बॉइलिंग पहुँचने के लिए कम एफर्ट लगाना पड़ेगा, कम टेम्परेचर लगाना पड़ेगा। कम एफर्ट लगाना पड़ा तो दैट मीन्स आधे टाइम पे मेरा काम हो गया। जो मेरा पानी 100 डिग्री सेल्सियस में उबल रहा था ओपन वेसल में, जिसमें लॉस भी था।
perform it without that, ma'am. It's just, you know, saving time.
It's okay. So saving time. So imagine open vessel, under pressure vessel. ओपन वेसल में सराउंडिंग के साथ हीट एक्सचेंजेस सब होंगे, लॉसेस भी होगा, पानी कम होता रहेगा, फिर दोबारा पानी डालोगे कि पानी कम हो गया है, उबली नहीं है दाल करके, परफॉर्म कर सकते हो। वाई प्रेशर कुकर? एफर्ट कम लग रहा है, आधे टाइम पे काम हो जाएगा। ठीक है, तो सिमिलर सिचुएशन। सो ट्रिपल पॉइंट इज द पॉइंट वेयर it exists in all three states together, whereas critical point is the point where liquefaction starts. Understand the difference, critical point, triple point. Clear?
Ma'am, you said the temperature is coming down from 700.
Yes, coming down from 700. So 500 will be reached first. Your answer was right. 700 से नीचे हो गए 650, 600, 550, 500, right? अब the relationship between the critical temperature, critical pressure and everything with your van der Waals constant A and B. Very rarely, sometimes this relationship can be asked. So you're supposed to remember them. So what it is, critical temperature is equal to 8A upon 27 RD, where R is your universal gas constant. Critical pressure is A upon 27 B square. And critical volume is your, what do you call that, Vc is equal to 3D. Now, there is introduced another term, Boyle's temperature. What is a Boyle's temperature is?
From the guy's body temperature.
Oh, Boyle's.
Boil.
So Boyle's law से रिलेशनशिप होगा, इतना तो समझ आ रहा है मुझे, ठीक है?
Pressure and volume.
Yes, प्रेशर एंड वॉल्यूम का ऐसा कोई टेम्परेचर जिस टेम्परेचर पे क्या हो रहा है?
But in Boyle's law we take temperature
Constant, yes. So at one particular Boyle's temperature something is happening. That is what I'm trying to say. क्या हो सकता है? अब मैं गैसेस के बारे में पढ़ रही हूँ। अगर लिक्विफिकेशन हो रहा है तो फिर मेरा क्रिटिकल टेम्परेचर क्या है?
Yes, ma'am. Gases. What can happen to gas?
लिक्विफिकेशन हो सकता है, और क्या हो सकता है? Boyle's temperature.
The container will explode.
No, nothing like that will happen. Think about it. What all scenarios can happen to a gas?
Ma'am, we are imagining that there is a volume of gas and pressure is changing.
Okay.
And we have to find out what's happening to a gas.
Yes. We have
Constant temperature.
Yes, constant. So at Boyle's temperature, something happens.
So Boyle's temperature
So
is a certain temperature at
Yes.
which
Something happens. So if I have pressure versus volume graph, at the Boyle temperature TB, something happens. What could possibly happen to a gas? Liquefaction I've already studied, critical temperature, critical pressure, critical volume. What else can
Is
happen?
it something related or intermolecular? molecules happen.
So you're meaning to say, so you are trying to say that above this the intermolecular interaction will decrease. But in Boyle's law we to consider that there is no intermolecular interaction.
Boyle's law. At a particular temperature. Ma'am, I don't understand, ma'am. We are taking temperature constant. So ma'am, at a particular temperature, ma'am, so it shouldn't really matter.
It shouldn't really matter, you're saying. So I am asking, can anything happen? Like when you have studied about it, can anything happen? So whatever you have studied so far, so the Boyle's temperature for any particular gas is basically the ideal gas situation. So above that temperature, it behaves like an ideal gas. That is your Boyle's temperature. Temperature after which real gas behave like a real gas behave like an ideal gas. That is what is referred as Boyle's temperature. Clear? So, now we come to the last part of the chapter.
Solid.
Solids we done. Liquids.
Ma'am,
Sorry. Gases we have done. Liquid. Solid state is in your 12th standard. Gaseous state is done. Now we come to liquid. What all do I know about liquid ever since I've been started studying liquid? These are the 5 things I know about liquid.
Ma'am, if we consider the volume and
It takes the shape of the container. So, liquids are composed of particles called molecules. The intermolecular forces of attraction among the liquid are quite appreciable. So that means they have interaction. That is why they exist in liquid nature. So that is they have strong intermolecular interaction. Compared to gas, the molecule in a liquid is relatively close to each other. So in gaseous space, I expected them to be diffused in all over the space. But in liquid, they are in the close proximity with one another. That is what I can say. The molecules are in constant random motion. I can say that also, even in the liquid there is a random motion, right? Otherwise there would have been solid state where there is a restricted motion. Average kinetic energy of the molecules of the liquid is directly proportional to the absolute temperature. So it's similar to gas, that it is directly proportional to the temperature. More the temperature of the liquid, higher will be its randomness, right? So that is. So these are the properties which I have studied from. Apart from that, definite volume, no definite shape, that I know from my starting. So the first property which I am going to study is about vapor pressure. So in order to study what is vapor pressure, let's say I am heating water in a burner in the open beaker. Okay? So after a certain time, it starts boiling. That means the water molecule has gained its kinetic energy and the pressure. So what is this vapor pressure means? That the sum of the particles have escaped the liquid state and are existing as vapors around that beaker, and that vapors putting the pressure on that liquid is referred as your vapor pressure. Evaporation is the process. It's a process. I am talking about the pressure exerted by the vapors of the water vapor onto the liquid surface is referred as vapor pressure. How it is, let's see. So if I see, the water molecules will be randomly oriented. When they are excited, the heat is given to it. Some of the molecules escape the surface, but they're still lying in the close proximity, because as soon as they go above that temperature, they'll again come back and condense down. You see the precipitation around your beaker and everything. Bubbles होते हैं, right? क्योंकि ऊपर का temperature कम होता है, नीचे का temperature ज़्यादा होता है. तो जिसकी वजह से तो दैट्स वाई वो वेपर एक प्रेशर बनाएंगे लिक्विड के ऊपर, उस प्रेशर को वेपर प्रेशर कहते हैं। ठीक है, अब इस चीज़ को समझने के लिए वेपर प्रेशर क्यों इतना इम्पोर्टेंट है हमें पढ़ने के लिए, वेपर प्रेशर क्यों इम्पोर्टेंट है। अब जब हम बॉइलिंग करते हैं, हम किसी भी चीज़ को, वाटर को ही बॉइल कर रहे हैं, हम कह रहे हैं ओपन वेसल में 100 डिग्री सेल्सियस में बॉइल होगा। क्यों 100 डिग्री सेल्सियस में बॉइल होगा, क्योंकि जो प्रेशर है, वेपर प्रेशर है, हमें उसे एटमॉस्फेरिक प्रेशर से इक्विवेलेंट लेकर आना है। एटमॉस्फेरिक प्रेशर क्या होता है, 1 एटमॉस्फेरिक प्रेशर। तो जब तक वेपर प्रेशर जो वाटर का है उस कंटेनर में, सो लेट्स से दिस इज माय कंटेनर, जब तक मैं इसके ऊपर का प्रेशर 1 एटमॉस्फेरिक प्रेशर तक नहीं लाऊंगी तब तक ये स्टीम में कन्वर्ट नहीं होगा, तब तक नहीं होगा। आई नीड टू वेट टिल दैट, and in order to reach that steam condition I need to supply heat, right? So vapor pressure is an important phenomena, that means it's an important phenomena where it can be applied. So let's say मैं पहाड़ों में जा रही हूँ घूमने के लिए पहाड़ों में जा रही हूँ और वहाँ पे मैं मैगी बनाना चाहती हूँ, मैं पानी रखती हूँ। अब मेरा पानी जल्दी बॉईल होगा कि कम लेट बॉईल होगा, लेट होगा। पहाड़ों में प्रेशर क्या होता है, कम होता है, ज़्यादा कम होता है। तो कम होता है तो कम एफर्ट लगेगा ना उस पानी को बॉईल करने में, बॉइलिंग पॉइंट पहुँचने में। जब मैंने एटमॉस्फेरिक प्रेशर कम कर दिया तो बॉइलिंग वाटर का टेम्परेचर भी, तो सेम फिनोमिना प्रेशर कुकर वाला, प्रेशर कुकर में पानी डाला, दाल डाला, सील कर दिया। प्रेशर कुकर मीन्स प्रेशर क्या कर रहे हैं, डिक्रीज कर रहे हैं, राइट। अंदर हम प्रेशर डेवलप कर, और ओपन वेसल में एटमॉस्फेरिक प्रेशर तक वाटर पहुँचना है, तो हम बॉइलिंग पॉइंट को लोअर कर रहे हैं बाय decreasing the pressure, right? That is what is happening. So that is how the vapor pressure is very important.
तो पहाड़ों में क्या प्रेशर कम होगा?
आप बताओ हाई ऑल्टीट्यूड्स में क्या होता है? कम होता है
जल्दी।
हाँ, क्योंकि मुझे एटमॉस्फेरिक प्रेशर पहुँचने, अब वहाँ पे एक और फिनोमिना आ जाता है, ठंड और टेम्परेचर जो होता है पानी का, यहाँ की तरह 25 डिग्री या 30 डिग्री का नहीं मिलेगा, वहाँ पानी मिलेगा मुझे 10 डिग्री का। ठीक है, मैं वो फिनोमिना नहीं, मैं अभी क्या पढ़ने की कोशिश कर रही हूँ, बॉइलिंग पॉइंट जो है लिक्विड का वो कम कर दिया मैंने बाय डिक्रीजिंग द प्रेशर। मैं ये फिनोमिना पढ़ रही हूँ, मैं ये फिनोमिना नहीं पढ़ रही कि 10 डिग्री का पानी उबालना है। ठीक है, 10 डिग्री का पानी 60 डिग्री में उबल जाएगा, वहाँ आर्बिट्री वैल्यू है, ठीक है, 60 डिग्री में उबल जाएगा। यहाँ पे जो 100 डिग्री में उबलेगा, सर्दी में ज़्यादा एफर्ट लगता है ना, तो वही वाली बात। सो अगर मैं सिचुएशन इमेजिन करूँ, दो सिचुएशन है वेपर प्रेशर निकालने के लिए। पहले मैंने क्या किया, किसी भी चीज़ को सैचुरेट करना पड़ता है, जब तक मैं कंटेनर सील नहीं करूँगी सैचुरेट नहीं होगा वो सिचुएशन। तो मैंने इसमें सिर्फ पानी भरा, ठीक है, पानी भरने के बाद इसे सील कर दिया। सील करने के बाद ये फिर अपने इक्विलिब्रियम में आएगा, कुछ मॉलिक्यूल्स उनके गैसियस फेज में जाएंगे, कुछ मॉलिक्यूल लिक्विड में जाएंगे, वो एक इक्विलिब्रियम बनेगा। उस इक्विलिब्रियम में पहुंचने के बाद वो जो प्रेशर होगा दैट इज योर वेपर प्रेशर। अब बॉइलिंग पॉइंट ऑफ व्यू से आते हैं, बॉइलिंग पॉइंट ऑफ व्यू से बॉइलिंग क्या होता है, सो देयर इज समथिंग रेफर्ड एज स्टैंडर्ड बॉइलिंग पॉइंट एंड देयर इज समथिंग रेफर्ड एज नॉर्मल बॉइलिंग पॉइंट।
स्टैंडर्ड और नॉर्मल,
yes, STP and normal boiling point. So the standard boiling point is at 1 bar pressure. STP, the condition is 1 bar, whereas normal boiling point is at 1 atmospheric pressure.
1 bar.
So generally for calculation we take 1 atm is equal to 1 bar for calculation, but that is not exactly the case. It is 0.98 something. So that variation causes the water temperature. Normal boiling point is 100 degrees Celsius. recommended boiling point is 99.8 degrees Celsius. Don't get angry with the scientists, it's okay. They are there to do their duty to and make you understand the difference.
Mom, why?
Why?
Just why?
So bar and atmospheric pressure has a difference of 0.02. Okay? And when we study under STP condition, standard temperature and pressure, then that thing becomes important. Okay? So, अब किस फिनोमिना पे मेरा वेपर प्रेशर एक्चुअली डिपेंड करेगा? वेपर प्रेशर इंक्रीजेस विद इंक्रीजिंग टेम्परेचर. व्हाट एम आई ट्राइंग टू से? जैसे ही टेम्परेचर बढ़ाऊंगी वेपर्स जो होंगे, जैसे अगर ये अभी मेरे पास 25 डिग्री पे है बॉटल, इस बॉटल को मैं 40 डिग्री में रख दूँ जैसे नॉर्मल समर डेज में होता है, तो ऑब्वियसली इसके अंदर जो प्रेशर होगा वो ज़्यादा होगा इन कंपैरिजन टू आज की डेट में जो प्रेशर होगा इसके अंदर. और यही मैं अगर इसे अच्छे से हिला दूँ तो मतलब मैं इसकी काइनेटिक एनर्जी बढ़ा रही हूँ, राइट? तो मैं इसका टेम्परेचर इंक्रीज कर रही हूँ जस्ट बाय व्हाट यू कॉल शेकिंग दिस बॉटल. So when I am shaking this bottle and making the temperature increase, that is also causing the vapor pressure to increase inside the bottle. So temperature का direct relationship, higher the temperature, higher the vapor pressure. Clear? Normal boiling point. The what do you call that? The definition of it. What is normal point? The boiling temperature where the pressure is at 1 atmosphere or 760 torr. So boiling point is a physical contact. It depends upon the strength of the molecule. कुछ molecules का बहुत ज़्यादा है, जैसे acetone, nail polish remover और thinner for that matter, whatever it is being used, paint को mix करके लगाते हैं. जब हमें paint करना होता है, thinner mix करते हैं to have that perfect consistency, right? So उसका टेम्परेचर क्या होता है? अगर मैं थिनर या एसीटोन की बोतल खोल के छोड़ दूँ तो इस टेम्परेचर में नहीं, मतलब समर डेज में उड़ जाएगा. यस, उड़ जाता है. सो अल्कोहल हो जाए, रबिंग अल्कोहल हो जाए, जैसे हम जब भी कोई इंजेक्शन या कुछ भी लगाना होता है, वी क्लीन आर द एरिया टू बी इंजेक्टेड बाय द रबिंग अल्कोहल. तो इनफैक्ट इवन फॉर सैनिटाइजिंग the alcohol which is used, the sanitizer, that also evaporate after you do. So that is due to the fact that they are highly
Alcohol.
They have low boiling points. They have low boiling. They are alcohol, but yes, they have low boiling points, right? So अब आते हैं ये जो मैंने एग्जाम्पल बताया था आपको, उसमें क्या कहते हैं, माउंटेन्स वाला जो एग्जाम्पल बताया था. बॉइलिंग पॉइंट चेंजेस विद प्रेशर चेंजेस, लेस प्रेशर लोअर बॉइलिंग पॉइंट. सो एग्जाम्पल, बॉइल्स लोअर एट हाई एलिवेशन लाइक माउंट एवरेस्ट और एनी पहाड़ फॉर द वेकेशन विच वी कैन गो, नॉट द माउंट एवरेस्ट फॉर श्योर. वाटर बॉइल्स एट 76 डिग्री सेल्सियस ऑन माउंट एवरेस्ट. So this is experimentally calculated by someone. This is experimentally calculated. Someone did that experiment after going to the Mount Everest probably. Or he created the Mount Everest situation in the lab. Either ways. Okay? Higher pressure, higher boiling point. Example, pressure cooker. Cooks faster because you cook at a higher temperature. So what is happening? You are creating a pressure inside it. You are making that vapor pressure being increased inside that pot very high. Thus makes the food cook faster. So these two are the application: high altitude as well as the pressure cooker. One more example. So if you remember, every biological lab for that matter, or any medicinal lab, or any apparatus to be used, even your dentist, the apparatus which he has to put it inside our mouths or put it inside our body, the surgical equipment, those all are autoclave. Now there is a new term which is being introduced, autoclave. Autoclave is a machine in which it's just like you can say a laboratory pressure cooker. It's a laboratory pressure cooker. So what it does is that you put all your apparatus, whatever you're going to use for the surgical thing or anything, put it in a bag. So there are sealable bags which are available. You put it inside, and you nowadays people are using UV for that purpose to eliminate all the germs. They put it inside the UV chamber, especially dentists. When the items required are very frequent, the autoclaving requires at least 2-3 hours of time. Okay, but UV is a short process, 15 minutes, it's done. You can use it. So, coming to autoclave, what happens in the autoclave is the water is pinned in such a manner at high pressure that only vapors of the water are moving around. The liquid state does not exist inside. It has made that pressure so high inside, the vapors are cleaning that apparatus. The steam, high steam. And why they are put it in sealed bag? Because when you take out that, you do not contaminate with your hands. Your hands have germs, irrespective how much clean you are, you're wearing the gloves or anything. When you're opening that machine, so that machine is this big, like a cylinder, and it has a rotating wheel which seals the pressure inside. So when you're taking out, they are kept in the sealed bags, Ziploc bags, and whenever in the surgery, whenever these things are required, they are opened at that time, after you have sterilized yourself.
Also, the equipments are put in a bag, and then the
bags are kept inside that machine, and in that machine the water is supplied.
The equipments are not coming in contact with water, so how are they getting?
So, steam can go inside
The bag.
Yes, it can. It can. Those bags are in that form. They are semi-porous. They are semi-porous only to the water. So you have those membranes which allow only one particular thing to pass out.
And ma'am, one more thing. Ma'am, we are not allowing our hands to contaminate the vapor, but
Yes.
there are the germs on the equipment.
So the steam which is circulating. So see, you have already cleaned the apparatus and you are putting it for the sterilization purpose. And you know high temperature kills all the germs. So you know bacteria or pathogens, any pathogens to survive. It requires an optimum temperature. And that is why it can make us the host cell. But if you are not providing that optimum temperature, you are providing a temperature which is very high. So obviously those bacteria cannot survive.
So those bacteria are still in the machine.
So what? They are in the dead state.
So ma'am, why do we say that we can't contaminate the steam by our hands? The pathogens or things on our hands will also die.
How it will die? You're not going to put the hand to the hot machine. When it cools down, then only you're going to take it out. You cannot take out the hot stuff from the machine. It's too hot, you're going to burn. You know, right? Steam burns are more dangerous than the normal burns. So it works in that way. So third application is the medical industry, surgeries, medical equipment. Okay. So if I see the graph, chloroform is 61.3 degrees Celsius, ethyl alcohol is 78, water is boils at 100 degrees Celsius. So this is your pressure and this is your temperature, and when the pressure reaches the 1 atmospheric pressure, then the boiling occurs, and that are the boiling point, normal boiling point, not the standard one. Okay. The next topic, which is surface tension. What is surface tension? Why am I studying this? Why is it so important to study surface tension?
It is a phenomenon which causes liquids to form like immense.
Yes. So if you see it in this bottle, you'll see it as there is a convex lens kind of a thing. You understand convex lens, I suppose, right? So if you see it, it will be like this. Why is that happening?
Surface tension.
Surface tension. So what exactly is happening is, why is it not getting clear?
I saw this thing in pipette.
Pipette.
Yes.
So you see in the, like right now the rain has occurred. You see droplets forming the spherical shape. That spherical shape is caused due to the surface tension. So what is happening is, when the molecule is present inside the liquid, then it's experiencing pressure from all over and net pressure is inside. But when it's in the surface, it is not feeling any pressure from above, but it's feeling the pressure from the inside. So what is it trying? The inner molecule are trying to pull the surface molecule inside. So when they try to pull inside, it forms a meniscus. That meniscus is due to the pulling. That pulling, and obviously pulling at the center would be more in comparison to the sides, because in the center there are more molecules in comparison to the side. That's why you get a curve. Clear? That is why the droplets are visible on the plant, on the bushes, on the car. If you see it.
But in this case, the low force is gravity, not the.
Both the things. Cohesive forces, adhesive forces. Both will come into it. Let's try to understand that. So what is this thing? Surface tension, first the definition. Surface tension is defined as the tension of the surface film of a liquid caused by the attraction of the particles in the surface layer by the bulk of the liquid. That is what I explained. The bulk of the liquid pulling the surface of the liquid, that tension which is experienced is referred as surface tension. Fine. It is due to the phenomena of the surface tension that drops of water tend to assume a spherical shape to attain a minimum surface area. So why is this happening? The spherical thing is happening due to the fact they are trying to lessen the surface area. Lessen the surface area by contracting themselves. By contracting themselves, they are trying to lessen the area around them. So let's see what happens next. So the spiders or the insects can walk on the water. You see, right? We cannot. But some insects, they can walk on uneven. You can see one of the famous example, paper clip. It's a metal, but if you put it inside your glass, it will float on water. You have seen that? So that is due to the surface tension. So what are so this is the clip, so the needle which is falling, the bubbles which you can see it on the plants, leaves and flowers, petals, especially when you get flower bouquet made for someone, you tell them to spray it with the water in order to look more beautiful, because they form the spherical shape, right? So these all phenomena are due to surface tension. Now let's see what is surface tension happening actually. So this is what I tried to explain. When a water molecule at the bottom of it, so it's experiencing the pull from all over, which is nullified, and it's experiencing an equal pull from all the angles. But when it is at the surface, it's experiencing pull from the half of the angle, but other half is normal. There is no pressure. That is why this pull is pulling this liquid down, thus causing a layer like this. Clear? So I told you about the two forces which are acting. Cohesive forces and adhesive forces. What are these? Cohesive, adhesive. You have heard about these terms. I'm not reading it and telling it to me. What are cohesive forces? What are adhesive forces?
Cohesive forces exist between molecules of same substance.
I should have opened the slide then.
Adhesive between
So that means water-water interaction.
cohesive.
The container and the water interaction, adhesive. Okay, so that means two type of forces are acting on this. So I see a rise. I see a rise at the side, and I see a pull at the center. So these are due to both the forces which are acting together. Both the forces. So what is it saying? Are intermolecular forces which causes the tendency in liquid to resist the separation. So the inside of the molecule are resisting the separation. That's why they're trying to stay closer. Secondly, the adhesive force is the attractive forces between the unlike molecule. So the container and the water, unlike molecule. They are caused by the forces acting between the two surfaces such that the mechanical forces sticking together and the electrostatic forces are opposing each other. So when they are opposing each other, they are trying to increase the surface area so that they feel the minimum pull. And they are trying to minimize the surface area so that they feel the minimum pull. So both are acting together. So the surface tension phenomena is very much clear to me. Where is it applicable? That is also clear to me. Right? क्या बचा है? Viscosity. Last phenomena है, पर वो आज नहीं कराऊंगी, टाइम नहीं बचेगा. Viscosity is big. Viscosity is big. I'll just introduce it. Next class, anyways, we are going to do certain questions as well, stating that कि इस चैप्टर को कंप्लीट कर देंगे इस हफ्ते. अगले हफ्ते थर्मोडायनेमिक्स. ठीक है? So cohesive forces among the liquid molecule is responsible for the phenomena of surface tension. So if at all a question arises, which phenomena is responsible for surface tension? Cohesive forces. Adhesive भी दे रखा होगा. Cohesive will be your answer.
Molecule surface है. हाँ.
ठीक है? Bulk of the molecule trying to pull together, having that spherical shape, is only possible due to the cohesive forces. रोल नहीं है. अब अगर मैं viscosity को समझा जाऊँ, पेपर क्लिप वाला एग्जाम्पल समझाया मैंने सरफेस टेंशन के लिए. अगर मैं viscosity को समझना चाहूँ तो एक मेटल बॉल लूँ और एक लिक्विड में डिप करूँ. 3 डिफरेंट लिक्विड. लेट्स से शुगर सिरप, सॉल्ट सिरप एंड हनी. 3 है. तीनों में मैंने एक मेटल बॉल डाला, तो क्या होगा? तीनों बॉल.
शुगर सिरप, सॉल्ट सिरप में बहुत जल्दी चला जाएगा.
So the motion, the speed of the ball would be fast and it will come to the bottom of it very fast. Then sugar is viscous. मतलब viscosity defines the fluidity of any molecule. Fluidity, कि कितना fluid है वो molecule. कितना fluid है, that means अगर मैं sugar syrup में डालूंगी, sugar syrup is also quite viscous in nature, but it will not be as viscous as honey.
हम honey में वो शायद reach भी ना करें.
Yes, so honey, so हाँ कर सकते हैं, बहुत टाइम लगेगा, बहुत टाइम. हनी कैसा होता है? जब आपको बॉटल से भी निकालना होता है, you have to make an effort to take out honey from the bottle as well, right? And it's very sticky and gooey, right? It's very sticky and gooey, and it makes the hand as well sticky and gooey. So when I'm going to insert the metal ball into that, so obviously it's going to make the ball has to make more effort to get penetrate into the bottom of it. So there is a 3 solution which I gave it to you, and all the 3 solution has different rate of that ball reaching the bottom of it. That is due to the phenomena of viscosity.
Ma'am, can we use this phenomenon to make bulletproof materials?
Very unreasonable question, not required at this point at all. Not in the point of view of this topic.
Ma'am, if you think about it, ma'am, bullet would take time.
So the purpose of the bullet is lost. What is the purpose of the bullet?
Ma'am, we are
one shot.
Ma'am, we are talking about bulletproof. Ma'am, our purpose is to stop the bullet, not to allow it to kill our.
So in that case, so let's say something is traveling with such a high speed, and you are wearing a honey mask. You are wearing a honey shield. So you really think so that bullet? So right now I am dropping the ball in the against the gravity. That's it. That is 9.8 meter per second. The bullet which is traveling at 150 or I don't know whatsoever, 1000 probably. You really think so the honey would able to solve this?
Ma'am, if the layer is very
So how much layer can you wear? Like I'm already this high, so you're going to wear this much, and you're going to go in a combat war to protecting yourself and fighting that war? Not possible. Not a feasible situation.
Okay.
Not a feasible situation. So the phenomena cannot be applied. You can use the hardest metal for this purpose, but not this. Clear? So, where were we? Yeah, viscosity. So, viscosity is basically when I talk about fluidity. So that means when I'm pouring the liquid like this, how easily is it coming? So ketchup bottle, mustard bottle, either you have to like shake it a little bit in order for it to come out, right? So that is basically slipping off the layers. So let's imagine the liquid let's imagine liquid is existing as these layers. Okay, the ability for it to slide over one another is your viscosity. Ability to slide over one another is your viscosity. Clear? So there's only one thing which is left to tell you, the formula and the SI unit for it. Poise is the SI unit and eta is the way the viscosity is represented. So if I see viscosity, do I have a real life example to apply it to viscosity? Not the bulletproof. Not the bulletproof. Will you be applying viscosity in real life nature? So surface tension, we saw the real life example. Vapor pressure, we saw a real life example. Viscosity, any real life examples which you can think of? So that is your homework.
No ma'am, examples as in ma'am where we see it or ma'am where it can
Yeah.
be productive.
Yes, where it can be productive. So every phenomena we studied so far, we studied for the purpose that there is an application which is available. So like if I go on a high altitude, the boiling point changes. That was the phenomena where I related my vapor pressure to. Homework. So surface tension, how did I imagine it to? The spherical droplets or the pin floating on the liquid. That is how I related surface tension. Viscosity, which will I relate? If you can think about it right now, very well. But otherwise, think about it. Tomorrow we are meeting, so we can think about it. So because see, until unless I don't give you something, then you won't even open up your textbook, I suppose.
Ma'am, we are talking about viscosity. Ma'am, we cannot say that it could be high. Ma'am, it can be very low. So ma'am, we can say that it's flowing very quickly. Something like viscosity.
What is the application? I am asking. Dam, how only water is there, right?
Water is there, ma'am. It has a very low viscosity. Ma'am,
Okay.
it's flowing, it's falling, ma'am, with very high speed, and it's generating electricity, low viscosity. Example.
No, not possible.
Ma'am, there's a dam.
Okay.
Ma'am, it has a very
High altitude.
Ma'am, it's falling.
It's falling.
Ma'am, it has a very low viscosity.
So this is the phenomena which I use. This basically is the water energy getting converted into electrical energy.
No, ma'am,
But this is not a phenomena for viscosity.
Ma'am, if it was honey, ma'am, it would take a lot of time to flow
So
down.
see, when you're trying to explain me this, think about it. I am not going to have honey to me all over.
Ma'am, that's...
No. I am asking real life example. So see, in surface tension I gave you a real life example.
Ma'am,
In vapor pressure I gave you a real. I am asking. So think about it. Right? It's okay.
No, ma'am, we're talking about only properties. Ma'am, ma'am, for example, in this dam, ma'am, we are saying that water is being used because it's conducting electricity. But if it had not been less viscous, if then they would, ma'am, we wouldn't be able to generate electricity.
Why not? It will be flowing slowly. It doesn't mean that it will not flow.
Ma'am,
Viscosity
it will
doesn't.
flow. Ma'am, it
Viscosity
will flow,
doesn't.
but since it's flowing very slowly, ma'am, how will it generate electricity?
Why not?
Ma'am, it's the power.
So. Power is generated in the dam by falling it from the higher altitude, right?
Ma'am, potential energy to electrical energy.
Yes. So, whatever speed at which once it reaches the top, there is no thing which is stopping it. It's going to come as per its gravity. It's going to come as per its gravity. So there will be nothing which is going to stop it from coming down.
Ma'am,
What if it stops there only? Then your question arises that this cannot be applied. What if it stops there? Like there is no flow movement.
Ma'am, just imagine, ma'am, the honey is flowing.
I am not
slowly.
agreeing. I am not agreeing. Think about the real life situation. Take the help of the book. It's okay. Think about it. We'll be meeting tomorrow. We can have this discussion tomorrow. Okay? Fine. Thank you so much.
Thank you, ma'am.